Hi there, this is the Share S20, a SLAM LiDAR scanner. I have been working with SLAM LiDAR for more than 5 years now, mainly in my construction projects where I design and build tensile structures. Since I know plenty of architects and structural engineers, they will often hire me to scan buildings in 3D and then convert that scan data into CAD models, which is another way the LiDAR scanner generates income alongside my core business. If you know your way around CAD, it won't take more than half a day to turn this 200 square meters house into a solid model. And honestly, the money is better in construction projects than in mechanical parts. Buildings are worth more, and clients don't mind paying extra for that. For a project like this, you can earn over $1 per square meter. That works out to around $200 in under 4 hours of work. In this video, I will walk you through how I take LiDAR scan data and turn it into a CAD model. We will use this 3-story house as the example, and I will be working in AutoDesk Inventor. So this is the scan result from the Share S20. I used the firmware update that solved the round corner problem, but not the newest one that fixed uneven colors on flat surface. Honestly, having a solid color point cloud makes a big difference. It way easier to understand the model than when you are looking at a plain non-color version. The most important thing with scan data is that it doesn't drift, no rotation, no shifting. The walls between rooms have to stay parallel, and the floors need to line up from one level to the next. If not, your CAD model is going to end up a mess. In my review, I found that the Share S20 and the C1 are the only two LiDAR scanners capable of scanning this 3-story house in a single pass without drift. If your SLAM LiDAR can achieve that, you will need to scan floor by floor or even room by room and then align the data, which adds a lot of extra work. Before we jump in, I know a lot of viewers have been curious about Share Studio and 3D support. I have tested, and while I can't review the details yet, I can confirm it runs smoothly. For those who enjoy 3D walkthroughs, the release is coming soon. As for me, that's not where my business is, so let's shift back to what matters here: PointCloud post-processing. This is CloudCompare, a powerful freeware tool for post-processing scan data. In this case, I will just be doing two things: cropping the scan to remove unnecessary parts and leveling the first floor. To crop the scan, I will select the scissor tool, switch to polygon selection and draw the boundary. Once that's set, I hit delete and the unwanted data is removed. Next, I click on the translation tool, choose the Z-axis, and use the mouse to rotate the scan until the longer wall lines up with the X-axis. For alignment, I'm using the window edges as my reference. Next, I will repeat the process to level the first floor along its length, but this time I will rotate it along the Y-axis. Since the scan data has no rotational drift, once the first floor is level, the second and the third floors will also align correctly. This step is critical in pre-reverse engineering work. The scan must be level. It's also important to check the level across the width of the building. In this case, it's already aligned, so no further adjustment is needed. The scan data aligns to the floor where the scanner is first placed. during initialization. That's why it's important to choose a level spot for positioning the scanner. Next, I will move the center of the yellow bounding box to the origin. To do this, go to Tool, select Registration, and choose Move Bounding Box to Origin. Next, I will modify the coordinates of the ground floor. It says the C value is minus 4.77 meters. I will translate the point cloud upward by 4.77 meters, which set the ground floor at the 0 level. Click on the translation tool, select the TC, and then click on Advanced tab and input the value 4.77, and then click on Forward. Now the point cloud is moved up. Remember, if the floors or the wall lines aren't parallel, or if the building isn't standing straight, you will need to abort and rescan. Alright, now the scan is ready. I'm going to load it back into AutoDesk ReCAP for the next step. To import PointClouds into AutoDesk software such as Revit, Inventor, or AutoCAD, you will first need to use ReCAP to convert the LAS file into AutoDesk native format, RCP. In addition to file conversion, ReCAP lets you organize the scan data into layers that can be toggled on and off. I usually separate the floors and walls for each level. For this scan, that means 3 floors regions, 2 wall regions, and 1 roof regions. Once the layers are separated, I will export the project in RCP format, and at that point the scan is ready to be opened in AutoDesk Inventor. So I'm working in AutoDesk Inventor. First, I will head over to the Manage tab, click on Attach, and then pick the RCP files. You can also tweak the point cloud density with the Edit Attach Data command. And you can use the navigator tool to quickly turn layers on or off whenever you need. For buildings with multiple floors, it's best to start with the ground floor first. Since I only scanned the inside of the boundary wall, I need to measure the wall thickness right here at this spot, and it reached 125 millimeters. I'm starting by drawing a rectangle for the ground floor, then adding an offset to account for the thickness of the boundary wall. The offset value is 125 millimeters. Then I use the extrude command to pull it down to about the level of the parking ground. Next, I make a quick sketch to cut out the floor step at the front door. You will notice I always round the dimensions up in steps of 10 mm. Next, I cut out the floor step at the back door using the point cloud as my reference for the depth. Then I add the floor at the back of the house, making sure to include the offset of the boundary wall. This part is the extrusion for the underground water tank. Next, I make the floor level drop for the toilet. Though technically, I should do this after extruding the walls. Sometimes I forgot that step. Finally, I extrude the parking ground. Next, I create the wall for the first floor, placing it in a separate new part called wall number 1. Then I trace the wall lines and openings. Since this is a precast concrete building, there aren't any structural columns, only load-bearing walls. That means the wall thickness varies throughout the building. So you really need some background in construction to recognize different building types and understand the function of each part you are reconstructing. For example, this building uses pre-made door panels which come in standard widths of either 700 or 800 millimeters. Next, I extrude the wall up to the top of the second floor level, subtracting 150 mm to account for the floor thickness. And then I extrude the remaining wall panels. And then I change the wall color to transparent. Next, I create the wall at the front parking area. This wall also supports part of the second floor above it. I always round dimensions to the nearest 10 mm step for Share S20 and C1. Here I make a pattern cutout on the wall using the array command. This small rectangle is used to provide retalo support at the end of the wall. Because this wall section is symmetrical, I create a mirror plane using the two sides of the wall I have already built and then mirror the wall onto the opposite side. Next, I fill the void above the door opening and cut out the space for the windows. You can really judge the quality of a LiDAR scanner during reverse engineering. If the scan data drips, the model lost squareness and parallel alignment, and that problem will carry over into the reverse process. I have tested many SLAM LiDAR systems, and the results aren't consistent across different brands, even when they use the same LiDAR sensor. Here I crop out the point cloud in the front area so I can clearly see this window. Creating wall cutout is simple, straightforward process, provided you have a basic understanding of 3D CAD modeling. With the first floor modeling complete, I will switch back to solid color mode to check for any missing points before continuing with the second floors. Next, I will create a new part called Floor 2, positioned directly above the first floor wall. I projected the boundary of the first floor wall to define the outline for the Floor 2. Next, I will crop a small section of the point cloud to trace the ceiling and floor beam outlines. In this case, the floor and ceiling will be modeled as a single part. Since the first floor ceiling is at the same level, I can model it by projecting the cross-section of the first floor wall, closing the sketch around the stair area, and extruding it downward to the required depth. Next, I will create a cutout on floor 2 above the stair area and trim a portion of wall number 1. At times, I switch to solid mode to make the details easier to see. Next, I will create a new part named Wall 2 and project the lines from floor 2 to define its boundaries. You will notice that the service shaft becomes narrower on the second floor. On the second floor, some walls align directly above the first floor walls, while others become thinner as the building rises. The bathroom wall is finished with tiles, which adds an extra thickness of roughly 30 mm. You will also notice the perfect square alignment of the wall lines captured by the Share LiDAR scanner. In my previous video using the 3D Maker Pro Eagle, the scanner consistently lost tracking whenever I enter this bathroom. To complete the scan, I will need to mount the Eagle onto a camera gimbal. Here I have set the door width to the standard 800 mm panel size. Next, I will extrude wall 2 up to the third floor level, subtracting 150 mm to account for the floor thickness. Then I continue extruding the remaining walls on the second floor. Next, I will fill the void above the windows. You might be curious about how this works with a measuring tape. For each rectangle, you will need 4 measurements, 2 for the width and length, and 2 more to define its position. Achieving this level of detail requires hundreds of individual measurements. Once the wall is complete, I will perform an extrude cut to set the bottom floor level. I switch the view back to solid color to check for any missing sections of the wall. At the third floor slab, I create a new part named Floor 3 and define its boundary by projecting from wall 2. I create this slab in the same way as the one on the second floor. Next, I will model the ceiling by cutting the cross-section of wall 2 and lowering it to the required depth in each room. The ceiling depths vary across different areas on the second floor. With the third floor slab completed, I now create a new wall, a wall 3, positioned on top of the floor 3. As you can see, when I trace the wall lines, they remain parallel and square up to the third floor. I haven't encountered any irregularities like those I observed with other LiDAR scanners. Keep in mind, when scanning from a narrow space into a wider one, most scanners tend to drift. To avoid this, walk backward from the wider area into the narrower one so the scan remains stable. Okay, next I will extrude the wall up to the ceiling level, sketch the window cutouts and fill the voids above the doors. Although the transparent color can be a bit confusing, it allows me to see through the point cloud without needing to crop it. Next, I go back to the floor 3 and create a drop level cutout for the bathroom floor. With the third floor wall completed, I now move on to creating the staircase between the second and the third floor. Architects know that staircases are among the most challenging elements to model in CAD. With the LiDAR scanner providing abundant reference data, staircase modeling becomes much faster and easier. Even with a U-shaped staircase, the modeling process can be completed in under 3 minutes. After tracing the staircase profiles, I extrude them onto the wall face to form the structure. I can create a triangular shape steps by projecting the sketch and extruding it downward. I apply the same sketch tracing method to the riser and tread of the staircase on the first floor. Here I'm performing an extrude cut to form the triangular stair step. With the modeling complete, you can export CAD file as step or SAT and deliver it to clients for interior design or custom built-in furniture fitting. For interior scans like this, the accuracy alert from the Share C1 and S20 devices does not exceed 10mm. Because I'm using AutoDesk Inventor, I can generate 2D drawings from this CAD model in under 5 minutes. All that's required is to enter the drawing environment, place the model, and begin creating cross-sections. I can then save the 2D drawing in DWG format and deliver it to the client. Some of you may not have encountered this CAD feature before, but it's actually been available for more than 26 years. You might be wondering how I can confirm the accuracy of the S20 scan data. As proof, Here is a prefab steel project where I rely exclusively on the S20 for measurements. If the error exceeds 10 mm, the prefab frame will not fit and the tempered glass panel would be unusable. Errors at this stage could result in significant cost for me. Here's another demonstration of SLAM LiDAR scanning applied to a larger project, a prefab tensile structure that I designed, spanning more than 4,000 square meters and valued at over $1 million US. I rely exclusively on the SLAM LiDAR to scan both the entire site and the fixing points. There was no rework required, everything fit perfectly, confirming that the SLAM LiDAR outperformed the total station in terms of accuracy. Within the next few years, this device is likely to become the primary tool for the surveyor. Alright, thanks you guys for watching. I'll see you in the next video.